Hi again, AP Calc students. We're moving on to the second lesson on Chapter 5 here. And this is, again, part of the meat and potatoes of this whole chapter here on definite integrals. Now, yesterday we did some approximation of area under curves using rectangles. And so it did look something like this, where we had some kind of a function and we tried to use some rectangles underneath to approximate area. Well, we formalize this a bit today and specifically call this sum of rectangles Riemann sums, named after some German guy who came up with this idea. And we can write this sum kind of strangely like this. Now, you may or may not be real familiar with this. This is the Greek letter sigma, and whenever you see that, it stands for a sum, or in other words, adding up a bunch of things. So basically what we are doing here is adding up the areas of these rectangles. Now, this f of x sub I, notice on this picture here, we can split up all these rectangles into x1, x2, x3, and so on and so forth. So the little I here just represents that particular number. This is going to go from 1 to n, whatever we set n to be. In this case, it looks like n would maybe be about 7. So this f of x sub 1, that's actually a representation for, oops, got to get my pen going here. This would be actually a representation for the y values. Anytime you have f of x, remember that's a y value. And then this delta x here, as you can see by the diagram, that's like the width of each particular rectangle. So we could think of that as x. And so of course y times x is just the area of each one of those particular rectangles. And when we have the sigma in front of it, it just means the sum of all of those particular rectangles. That's just the fancy way of writing it. And so don't get too confused by this. It looks like a lot of mumbo jumbo, but we'll show you how it applies to integrals here in just a second. Alright, anyway, here's what we just looked at the last slide. Now we just put in front of here a limit symbol. Notice this is the limit as n approaches infinity. Notice here's n up here. And for our sigma here, we can start it at 1 and go to n. Now all this really means is that we can vary the number of rectangles under the curve. And as you might expect, the more rectangles we have under this curve, the better my approximation would be for the area. The smaller I can make this width, then it's going to fit more nicely under that curve and give me a better approximation for the area. So here's our limit notation again. We're just saying as this n gets bigger and bigger and bigger until the width of these rectangles gets almost negligible, I can essentially do that. Again, remember this f of x sub I, that represents the y value or the height of the particular rectangle, and the delta x is the width. Anyway, so if I have that particular limit here, now here's my representation for the definite integral. Right here it is. Notice we have this funny curly Q thing. That's the integral sign, or the integrand as we call it. We have an a and a b. This is your lower bound and upper bound, as you can kind of see from this diagram here. F of x is the actual function. Hi Adidas, you helping? Yep, Adidas is my assistant today. F of x is the y value. And you can kind of think of this dx, which we've seen before for derivatives, you can think of that as the width. So again, here's y and x, or height and width. Same type of thing here, height and width. And this is how we'll represent this from now on. This is called the definite integral from a to b of f of x dx. Now we wouldn't have to have an x here. If this was a t, we'd have f of t dt. Or if it was an n, f of n dn, that type of thing. But this is probably a key idea in the whole chapter, is that this representation of using rectangles to sum up an area is really the same as this definite integral type idea. Now, one interesting thing that we'll see is when we talk about area here, anything that's above the x-axis is considered to be positive area. Notice we have a couple regions here, but anything that's below the x-axis is considered to be negative area. So that's how integrals are defined, and we'll see that in action here fairly soon. Now let's just practice doing some really easy integrals here. And because they are areas, we like to try to draw these out or sketch these out a little bit. So we'll do that in this case. So first of all, I'm just going to try to make a little sketch of a grid here, and then I'll change colors here a bit, see what we can do. First of all, what is 3dx? Whatever we have right here, that's the function. So if I have y equals 3, of course that's just going to be a horizontal line like this at 3, and I'd be graphing that. What this is saying now, I want to see if I can find the area of this from -2 to +3. So what I'm really looking for here then is this particular area, and I'll sketch it in here so it looks just like this. That's really all I'm looking for here, the area of this rectangle. So fairly straightforward, I think, in this case, in that we have a length from -2 to +3 of 5 and a height, of course, of 3. So all we have to do is multiply 5 times 3 and get the value for this integral is simply going to be 15. That was pretty easy. That was our first one that we took a look at, though. Now let's move on to the next one here. Again, I'm going to draw a little grid here for us. This one, 1/2 x dx. Now 1/2 x is basically going to be, again, if you think of this as y equals 1/2 x, so that's a line that goes right through the origin like this. And we want to go from 0 to 6, so I'll just mark that out right here. And again, the area I'm really looking for here then is, let's see if I can find a nice color to use here. So the area I'm looking for is this. Notice it's really just a triangle. And how do you find the area of a triangle? Well, it's base times height divided by 2. So let's see if we can figure out some of this distance here. Obviously, this base here from 0 to 6 is going to be 6. And if I put a 6 in place of x, 1/2 times 6 is 3. So that's what's going to be up here. So that's going to be a height of 3. And so area of a triangle, of course, here's my other cat, Puma, laying on my left arm here. So in this case, it's going to be base times height. So 6 times 3 divided by 2, that's 18 divided by 2, which would be an area of 9 for that particular integral. So that's how we want you to be able to view these, especially at the start, is just remember that an integral is an area, and it's the area underneath that particular curve or that particular y value that we have there. Now you can also do this on your calculator. Here's a little bit more complicated example right here. This is the definite integral from -4 to 6 of the absolute value of x minus 2. Well, first of all, in our calculator we'll graph that. Should have an idea by now that when you have absolute value, it's that V shape. The minus 2 is just going to move it down 2 units. So this is what the graph looks like. If you go to your calculate menu, that second and trace, you should see this option. It might look a little bit different on your calculator, but sure enough, there's that integral, the integral of f of x dx. When you select that, it will ask you for the lower limit and the upper limit, which you can just type right in there. I've already typed in the lower one, and so the upper one looks like that. And when you press enter, voila, here's what your calculator should do for you. It will actually shade the region that you're trying to find the integral of, and it will even tell you your specific answer. Now keep in mind what we talked about before. If we did this piece by piece, remember this part would be positive, this would be negative since it's underneath the x-axis, this would be positive, but this is your overall value of the integral when we put together all those positive and negative parts. So that's a pretty slick way for your calculator to help you out here. Obviously we'll be doing that quite a bit. And just looking at the same function in another way to use your calculator, you can go to the math option, and sure enough there's that numerical integral. Just like you remember we had this numerical derivative last couple units, we have a numerical integral. Now yours again might look a little bit different. On this calculator, when I select that, I actually get an integral looking symbol like that. You may get something like let's see if I can get my pen going here. You may get something like this. Might say fn int, and then you'd have to actually enter in that function like this. You'd have to put what variable we are integrating it with respect to, which would be x, and then you would put in that lower limit and upper limit like that. Again, on your calculator you might have to do something like this. I would try to practice on that now and make sure you can find that. But anyway, as you can see, we do get the same value right here that we did, and so that's good. That's just another way of evaluating integrals. So we'll be practicing on this a lot in class. You'll become very familiar with the notion of the definite integral. Alright, thanks for watching everybody, and we'll see you guys in class.